Hello, now we are all here. So thank you for joining, everybody, wherever you're joining from. It's a pleasure to host you. As you might have hint from the description of the event, today there is going to be a joint collaboration in the explanation of a real case in between Hexagon and Newtwen. With me, there will be Giorgio, Thomas, and Francesco, that are respectively the lead machine and drive engineer for Hexagon, Giorgio, the senior technical consultant for Cradle CFD, for Hexagon again, and then it will be Francesco, that is basically the founder and CEO of Newtwen. So we have been working together in the past months to basically define and understand how to apply virtual thermal sensing technology to onboard chargers, and today we have a case to unveil to you on how this actually has happened, what we have done, what actually Hexagon has been doing on the onboard charger, what Newtwen has been doing, how we have collaborated together. And we hope that this will shed a new light technically on what is possible on that kind of systems and subsystems. Without further ado, I would ask you to, if you have questions, to put them in there is a Q&A tab. You should see it up in the Teams tab. So please use the Q&A tab at any time or moment to gather your feedbacks or questions. We're going to review them on the back end, and then at the end we are going to try to answer to all your questions. In case there are going to be either too many questions or not enough time, we're going to answer to you by email. So please feel free to just share any comment or question or doubt in the chat. Without further ado, I will leave the word to the Hexagon team to start giving us a perspective on what actually we have been doing together at the onboard charger level. So thank you, everybody. I'm going to be back for now. I'm leaving the floor to the Hexagon team.
Can you see my screen?
Yes, we can.
Perfect. So good afternoon to everyone, and thank you very much, Giuseppe, for the nice introduction and for inviting us presenting at your event. So my name is Giorgio Valente, and together with my colleague Thomas, we'll talk about the onboard charger design and the thermal analysis that we did for this collaborative project together with Newtwen. So let's go through the agenda very quickly. So I'll first give a brief introduction of the Hexagon Manufacturing Intelligence division. Then I'll also introduce briefly the Hexagon Applied Solution Group. And I'll describe the case study that we selected for this collaboration, which is the onboard charger. Thomas will give you an introduction of the Hexagon CFD tool called Cradle. And then I'll show you the thermal analysis that we did on the onboard charger using Cradle, experimental validation, and then the interface with Twin Fabrica by Newtwen. So let's start with the introduction to Hexagon MI and Applied Solution. So Hexagon as a whole is I would say a pretty big company. So we are almost 25,000 employees worldwide, and we have it's divided into several divisions, as you can see from the screen here. The division where both myself and Thomas are working is called Manufacturing Intelligence. The main business of Manufacturing Intelligence division is essentially selling CAE software, and Cradle is one example, selling production software, selling metrology devices, and providing engineering services. And this last bit, the engineering services, is where the Applied Solution team comes from. So essentially, the Applied Solution group is the responsible team for delivering engineering services. We are about 40 odd engineers. We can cover pretty much all aspects of powertrain design or optimization or analysis. So we have a mechanical team of engineers with over 30 years experience in designing transmissions. They actually started in the late 80s with wind turbines gearboxes, and then moved into transmission for automotive, aerospace, and so on. Then we have capabilities of electrical machine designing, power electronics, control system, and overall system integration. The kind of project we do could be from clean sheet of paper design, where we start from scratch with concept design, detailed design, and then we build the prototype and we test it. But we can also do, and often do, sort of more specific projects where we optimize certain aspects of a customer powertrain, or we solve specific issues. Okay, let's move now to the next step, the description of the onboard charger case study. So this picture here shows a nice 3D view of the onboard charger that we recently developed within our team, the Applied Solution team. On the right, you can see the main specification. So nominal power is 11 kilowatts. And we have a voltage on the AC side of 230 volts phase to neutral. Output voltage on the DC side can be configured to be either 400 or 800 volts, depending on your battery voltage level. Number of phases can be single phase or three phase. Power flow is bidirectional. So you can use this converter to for the main purpose of charging the battery, but you can also use it to supply the grid in the so-called vehicle-to-grid operation. For the cooling system, we have a water cooling system, and then we selected discrete silicon carbide MOSFET. For this first prototype, we went for 3 separate PCBs for the 3 main stages of the converter. So we have an input stage with the AC line filter. Then we have an AC to DC stage, which essentially rectifies voltage and current. And then we have an output DC to DC stage, which connects to the battery. This slide shows a little bit more details on the different stages of the converter. So on the AC line filter, we implemented an LCL filter and a common mode choke. And then we also installed a pre-charge circuit and the protection fuses. We then have the AC to DC stage with which is basically a 3-phase full bridge converter with the neutral as well. And then we have the DC to DC stage, which is a fully bidirectional full bridge CLLC topology. It's essentially symmetrical, so it's fully bidirectional. And we have a transformer that can be, depending on how you connect the winding, you can have both, you can have either 400 volts or 800 volts output, which is based on your on the batteries that you have. Within this project, we also developed our own control board and developed in-house software. So the control board was basically designed around the Texas Instruments C2000 DSP. It's fully flexible in its design. So in this case, we are using it to control the onboard charger, but you could use it to control a traction inverter or a DC-DC converter and so on. We actually have 8 ADC input, 4 sigma delta ADC digital inputs, and 8 PWM outputs. We also installed a 4-pin automotive connector with additional analog and digital inputs and outputs, so that a customer can customize the board for a specific design. We have, of course, CAN bus connectivity, very important for automotive, and also we implemented an interlock circuit. As I mentioned, we also developed the in-house software with this project, including both the base layer of the software, essentially programming the low-level peripherals, and the application layer, which in this case, for this specific project, is the control of the onboard charger. So as I mentioned, we started from clean sheet of paper. So the first step was, of course, to the selection of the converter topology. And then we did an extensive optimization using Plex. So this was a script-based optimization where we essentially selected the best values of passives, like inductances and capacitances for the ADC to DC and DC to DC stage to maximize efficiency. We also used Plex to validate the control of the onboard charger and to validate the overall behavior. And we also used, we developed the C++ code, and we tested it in Plex using the C script blocks. So then basically we could just copy and paste them into the into Composer and then deploy them into the DSP. So before jumping to to show you the thermal analysis results, I'll let Thomas give you a brief introduction of our CFD software, Cradle. Thomas? Yeah.
Thanks, Giorgio, for the introduction. So I'm here to present our dedicated CFD solution for electronic applications, especially when the electronic cooling applications become complex. So what are the challenges? We've already seen on Giorgio's slides that the inverter design and also the PCBs are quite complex geometries. So if you go in with traditional CFD, you need to handle with vast CFD files with 2,000 up to 5,000 separate parts. But you also have your PCB designs, which come from different design systems, from ECAD systems, like Altium Designer or Zuken. So the challenge is to bring these various sources of geometry together to handle these huge geometries, megabytes, gigabytes of data, and then to come up with an accurate simulation for that. And as all engineers which are already familiar with electronics cooling simulation know, that it's all about getting a precise estimation of the local thermal conductivity in the PCB. So this is the core. And then, of course, you need to come up with accurate results in a reasonable amount of time. Afterwards, it's not only about thermals, it's about multiphysics, like condensation, it's about Joule heating. So it's not about the flow itself. All right, next slide. So these are the challenges. What is our solution? So the solution of Cradle CFD is that we can natively read not only CAD files, but also the ECAD files. And when I talk about ECAD files, it's not about Gerber or drill data. It's about mature ECAD formats like ODB++ and IPC 2081, which means you don't have to build up again the layers of your PCB in the thermal analysis tool, but you can import the PCB as it is and start running your simulation. We have an unconventional meshing approach, which is an hexahedral meshing approach. And this has the advantage, you can mesh, you can see an inverter on the upper right picture with thousands of parts and a mesh of 93 million elements. And this was meshed in 1.5 minutes. So this all comes together under the term of productivity. So you can import your CAD, you set your materials, you set your heat sources, you mesh, and you run the simulation. And of course, Cradle CFD is on a market for not only since yesterday, but a longer time. We have all kinds of multiphysics involved, like condensation, like liquid cooling, like Joule heating, and many more. So on my third slide that I have, I just sum it up. What are the benefits of using Cradle and why are a vast number of customers already trusting Cradle for more than 40 years? It brings the thermal engineer to a point where he spends his time in analyzing ECAD designs, in analyzing inverter designs, producing solutions, producing thermal results, and not in CAD cleaning and not in model simplification. Thank you.
Thank you very much, Thomas. Very, very nice. So let's go back to the onboard charger, and let's now look at the thermal analysis that we did using Cradle. So at first, we started with actually trying to optimize the PCB. So we ran thermal analysis at the PCB level. To do that, we used Altium Designer to design our PCB. We exported the Gerber files there. We imported them into SCStream. By the way, SCStream is one of the packages of Cradle, specifically for electronic simulation. And we ran the current analysis there, the electric current analysis. So as Thomas was saying, it's multi-physics, so it's not just for thermal simulation. You can also do current analysis, and you can see some results here. So basically, you set your boundary conditions for the current analysis. You run the simulation. You get these nice column maps that display essentially the current density distribution on your board. You get the joule heat source for your simulation, and then still within SCStream, then you can run the thermal analysis to get the temperature distribution. So as a first approach, we started with having all the 6 layers with the same thickness, 35 micrometers. And we weren't very happy with the first iteration of the design because we were getting quite high delta temperature initially. So we decided then to go for option 1, which is essentially simply doubling the thickness of the copper for each layer. So we went from 35 micrometers to 70 micrometers, and this immediately improved the results in terms of temperature, maximum temperature on the PCB. However, of course, you also double the amount of copper. So iteration 2 was then to go back to 35 micrometers thickness and optimize the routing itself within the PCB. So we tried basically to remove the current choke point, and we still obtained reasonably good thermal performances at the PCB level. And of course, with the advantage of saving money because you have less amount of copper. Let's now look at the CFD simulation results at the converter level. So for this bit, we imported the IDF file format. The IDF file format is essentially a simplified CAD geometry compared to, for example, stat file. So we could also import stat file, but you will have much more details and they will be more difficult to handle in large simulations. So IDF files essentially is what you can see here on the right. It massively simplifies the geometry of your converter. And we then model the devices within SCStream. So we also model the internals of the devices. So you can see here, we model basically the mold, which is the plastic encapsulating the internals. We model the plate, the leads here, and the chip area, which is actually where you apply the losses on your device, and then the bonding between the chip and the plate. And we then model the thermal interface material between the MOSFET and the cold plate. Then still within SCStream, we also model the cold plate. So for the cold plate in this project, we went for an off-the-shelf aluminum cold plate with a copper pipe, essentially with 4 passes, as you can see here. And we modeled that in SCStream. We set the boundary conditions with 5 liters per minute flow rate and 60 degrees C for the inlet temperature. And these are the kind of results that we can then visualize from the post-processor once you solve the simulation. So in this case, I hidden most of the components just to focus on where the hotspots are. So I basically just left the 6 devices here. We can also further look into the details of where the hotspot is by removing the mold from the device. So here we can see the maximum temperature is actually on the chip area. Now you can look, for example, also at the cooling water and how it increases in temperature as it absorbs all the heat away from the devices. Few more results from the CFD here with the pressure distribution in the cooling pipe and the velocity field in the cooling pipe. This last one is very important for this work because that's one of the inputs to the Newtwen software to Infabrica. So it was actually exported and then shared with Newtwen for their reduced order modeling. Next is the experimental test. So of course we built the prototype, and then we took it to the laboratories at Sheffield universities where we performed all the testing. We built this nice test rig that you can see here in these photos. We glued the thermocouples to be able to measure the temperatures at the device level. So we had a total of 16 thermocouples. 10 of them were actually glued on the case of the MOSFETs, as you can see from this picture. Then we had a few more on the cold plate and on the PCB, and 2 of them to measure the inlet and outlet temperature, the cold plate. And then we had a flow meter sensor to measure the flow rate of the water. So we ran an extensive experimental campaign where we essentially varied the load that we were applying to the OBC. We varied the inlet temperature. So we had a chiller that we could use to set the inlet temperature for the water. We varied the flow rate, and we collected all these nice test data that were then also shared with Newtwen to be used to calibrate the reduced order model, as Francesco will show you in a minute. Finally, just wanted to summarize all the the overall interface that we have with Newtwen, so with their software to Infabrica. So these are the kind of data that we exported on our side. So first of all, the CAD geometry of the full converter. Then we exported the mesh and we shared it with Newtwen, materials properties, boundary conditions, loss model for the specific device that we used, CFD solution, as I showed you before with the velocity fields, and the test data is very important for the calibration. And with this slide, I conclude my presentation. So again, feel free to drop any question you might have in the Q&A bit. And now I'll leave the presentation to Francesco, who will talk about virtual thermal sensing.
Thank you very much, Giorgio. I'm going to share my screen as well. Can you see my screen? Also in presentation mode?
Yes.
Nice. Well, thank you for the kind introduction. The main scope of our collaboration project was to basically bring high fidelity and complex simulation created by Cradle CFD on embedded target application like the Texas Instrument microcontroller unit in order to, let's say, enhance the thermal management and to measure the temperature also in critical and inaccessible, usually hotspot like in the MOSFET discretes. That was the main target of our collaboration. So once again, I will talk briefly of what virtual thermal sensor is and how Infabrica can be used to basically build and deploy them at scale on different applications. And we will see together all the say technical passages in order to arrive there. So Why it's important to have the temperature knowledge with a high level of insights. So for example, to try to estimate in real time with high accuracy over all the operating conditions and over all the boundary conditions for this application like onboard charging, it's so relevant. It's relevant because it's relevant for the efficiency of the control, for the performance, for fast charging, etc., etc. But unfortunately today, for, let's say, the production, the state of the art of hardware sensor, let's say, can't basically achieve the kind of insights because you can't measure directly the junction temperature of the MOSFET discretes. You can't implement as many sensors as you would like the one in the experimental setup that we have done together because of cost constraints, etc., etc. So this lack of information in real time today brings to use in the control oversized safety margin that at the end they jeopardize the performance and the efficiency of the control itself. So virtual thermal sensor technology is something new, and you can consider them as software sensors that they don't have sensor placement limitation. Basically, they can be placed wherever you want without any kind of hardware limitation and constraints. They can predict the temperature behavior with high accuracy, and they can be compared in terms of accuracy with the real sensor, basically. So to create them, we have worked among let's say more than 10 years of research in Newtwen on a new methodology which is composed by 3 main steps. So usually we start from the so-called high fidelity models, the models used for design purpose. So models as designed, I'm talking about finite element models, CFD simulations, etc., etc. So models that can really represent the physics. They have a high level of details of the geometry, but let's say they have the curse of dimensionality. Basically, they are models that are good for design purpose, but they are not good enough because of their complexity in terms of computational effort to be implemented in real time on the microcontroller unit where the control is implemented. So basically, the first step is to start from these high fidelity models and compress them enough in order to achieve the real-time feasibility, but holding the accuracy and the resolution. And to do that, you need to use advanced model order reduction libraries that are capable to really reduce the computational effort, like in this case, passing from 0.4 million of equations, so degrees of freedom, to just a set of 30 differential equations, which represents our reduced order model, and then it's light enough and accurate enough to be implemented in real time. So let's say that at this second step, what we have achieved, it's a compressed version of our high fidelity model, but still, we know that when we are talking model as design for simulation, usually we need to, say, arrive at some compromise in terms of geometry accuracy. We don't know with 100% of certain the material properties. Some boundary conditions, they are, let's say, unknown, like flow rates usually are not measured in real time. So basically the thermal behavior changes a lot if the flow rate of the coolant system changes. So all these kind of unknowns and uncertainties in the system bring some error and some, let's say, mismatches and discrepancies between a model as designed and the model as manufactured. So in order to, let's say, enhance our reduced order model, to transform it from as designed to manufactured, we need data. And the other, let's say, data that we have received from Hexagon team was the test bench experiment setup. And we have leveraged our artificial intelligence techniques coupled with our physics-based reduced order models in order to enhance the accuracy and to obtain a unique model capable of predicting in real time with high accuracy and in all the operating conditions the onboard charger under test. And then the final code must be exported and implemented on a microcontroller unit. So these are the main steps that you need to perform in order to implement in your system a very accurate virtual thermal sensor. And let's say that you are reliable enough to be used basically in closed loop control for thermal management. And Newtwen has worked in the past years to encapsulate all the technologies, all the know-how needed, and all the resources, the computational resources that needed to basically build and deploy at scale on different applications, from onboard chargers to full traction inverters, electric motors, etc., virtual thermal sensing technology for embedded applications. So our product, Twin Fabrica, encapsulate all the steps needed to create and deploy virtual thermal sensors on embedded hardware applications, starting from a high fidelity full order model. So let's see with high details the onboard charger application here. Working together with Hexagon, we have basically identified which are the main key performance indicators to be achieved during the activity of bringing high fidelity simulations on the edge, so on the microcontroller unit. First of all, the kind of resolution. We want to have 10 virtual thermal sensors implemented the closest possible to the discrete MOSFETs. And in this case, we have 8 virtual thermal sensors for the DC-DC stage and 2 for the AC-DC stage. Then the accuracy, of course, if we want to, let's say, use this kind of advanced insight in real-time control, we need to achieve a high level of reliability, and it means a high level of accuracy on the range of plus minus 5 Celsius degree of error, of max error in all the operating conditions, so steady state, transient for different level of currents, voltages, switching frequency, but also for all the boundary conditions. So I'm talking about different flow rates, different coolant temperature, different ambient temperatures. So the second constraints, apart from the accuracy, was the computational effort. So basically the memory footprint and the execution time. If you want to use this model in real time, the memory must be lower than 40 kilobyte for this kind of application. And most importantly, the execution time of the virtual thermal sensing must be lower than 200 microseconds, so covering less than 2% of the task of the microcontroller unit where this kind of virtual sensing technology must be implemented. And in this case, it was the 10 millisecond task of the microcontroller. So these were the KPI to be achieved for the overall project. So as Giorgio has already mentioned, we started from the input coming from Cradle CFD software. So basically, we have imported the geometry mesh from the full order model, but also the velocity full fluid solution already solved inside Cradle, and they could be easily imported inside Twin Fabrica, where you can set, you can import the mesh, you can set material properties, you can set the boundary conditions, the operating condition, the Joule losses. You can also import the current density and power loss distribution inside geometrical entities, etc., etc. So once the high fidelity model in this case was already done, is imported inside Twin Fabrica, we need to perform the first step, that was the model order reduction techniques. But before to arrive there, I want to mention that inside our software, you can also model the advectivity transfer coefficient. That's why we needed the velocity fluid field to be integrated inside the software, which is quite relevant in order to consider this kind of, let's say, heat transfer component in the heat equation, in the partial differential heat equation. So our model order reduction technique is quite, let's say, unique because it can also handle this kind of component in the partial differential equation. And so our model order reduction inside Twin Fabrica, they can really handle this heat problem. And the kind of reduction that I'm talking about was passing from more or less 400,000 of equation into a set of just 30 differential equation to be solved in real time. The other main functionalities that Twin Fabric allows to do is the basically the error analysis of your reduced order model. Since it is a reduced order model, the solution, of course, is not a temperature, but model order reduction allows you to preserve the full resolution of your geometry. In fact, what you can do, you can solve transient simulation, frequency domain simulation, or steady state simulation in the low rank field, so in the reduction rank space where your reduced order model lives, basically. And you can always reproject the reduced order state into the full mesh. And here you have a practical example of what I was meaning as error analysis that you can double check inside Twin Fabrica. So basically here just putting a set of material properties, heat sources, and boundary condition in the system, you can solve both the full order model. So we have also a finite element analysis solver inside Twin Fabrica, and also perform the reduced order model and then reproject back in the full mesh to see if the distribution of the temperature is preserved. And this is quite important for the second stage for our, let's say, virtual sensing technology, because the second stage is the sensor placement. So in order to transform a modelless design into a modelless manufactured, we need to match the real data, the real experimental setup, right? So here we need to, let's say, optimize the correlation between the test bench experiment setups, and in this case, we had 10 thermocouples glued in the DC-DC stage and AC-DC stage. So what we had to do inside Twin Fabrica, we had to select the node of the mesh as close as possible where the real temperature was placed in order to optimize basically and calibrate the parameters of the reduced order model and to basically enhance the accuracy of our virtual thermal sensors. So here we have placed 10 virtual sensors exactly corresponding with the real test bench experiment setup, which is quite relevant because it's another, let's say, feature which is basically superior to the classical thermal network, where you don't have this kind of geometry resolution because basically the geometry is not well preserved. It's just you just have an equivalent electric circuit, and each node of the thermal network is just basically correspond to a volume average of a certain domain. While inside our tool, you can exactly place a virtual thermal sensor as close as possible where your real sensor is. And this is relevant for the calibration of the reduced order model itself. So once the virtual sensing is basically set up as close as possible to the real one, of course, we need to import the data. In this case, we had more than 3 hours of recording of data in the test bench. So more than 10 different load conditions, 4 different fluid flow rates conditions, 4 different coolant temperature conditions, and the recording of these, let's say, 10 sensors. Here we have an example of the transients simulation, the transients experiments with the data input and output. So we were recording the current, the DC voltage, the AC voltage, the temperature in the board, and then the temperature of the 10 thermocouples as output. So the goal was to obtain a unique model capable of predicting the temperature among, let's say, all different operating conditions and boundary conditions without knowing nothing regarding the flow rate and the temperature of the coolant. That was the main challenge, basically. So as first step, we have performed inside Twin Fabrica a calibration. So using the parameters of our reduced order model, these parameters have been optimized, so solving an inverse problem. So there are many solver optimizations inside Twin Fabrica that can be used to do this kind of task. And the scope is to find the best set of physical parameters. I'm talking about thermal conductivity, specific heats, mass densities, heat transfer coefficients, such that basically you can reduce the error between what you're estimating in real time and what you're measuring. So here we have a kind of example of a test used during the calibration. where the solver is finding a set of physical parameters such that our model can predict properly what is happening in the real test bench setup. Here on this calibration test, the error was, let's say, the maximum error was around 5 Celsius degree, so inside the tolerance that Hexagon has required. But if we change test like this one, so if we validate the kind of, let's say, accuracy of our reduced order model within a test that is never used during the calibration procedure, we can observe that in some cases, for some time horizons during the transients, the error exceeds the tolerance of 5 Celsius degree, because in some cases here, the error is superior to 5 because it is 7. And so we need to, let's say, enhance our model with something more. But this is something, let's say, normal, because what we are asking for the moment to our physics-based reduced order model is to identify a set of boundary conditions such that it can represent multiple boundary conditions, which is, let's say, not possible. So how to mitigate, how to cover boundary condition unknowns, non-linearities that have not been included in the physical model, material properties that are not certain that are, let's say, uncertain in the system. All this kind of, let's say, stuff can be mitigated by means of data-driven models that we have implemented a special architecture, an AI network, already pre-configured inside TwinFabrica, so you don't need to be a machine learning expert or an artificial intelligence or a data scientist to create this kind of, let's say, discrepancy models. And why discrepancy model? Because it has the job to cover what the physics can't in this case. So the discrepancy model, basically, it's calibrated to enhance the physics-based reduced order model to increase the accuracy, covering all the aspects that I've mentioned before. So the unknowns boundary condition, the uncertainties in material properties, and the non-considered non-linearities inside the physics-based reduced order model. So inside TwinFabrica, you can, with one click, easily calibrate this kind of final model architecture. And these really enhance the accuracy of your system. So in this case, this is a validation test that our final model architecture, composed by the physics-based ROM and the artificial intelligence discrepancy model, can achieve. So in this case, in all the validation tests, the error was less than 5 Celsius degree, achieving the target accuracy KPI. So let's see then, as last, let's say, point, the accuracy has been achieved, but the other constraints was on the computational effort, right? So this final architecture, which is composed by a power loss model, a thermal physics-based reduced order model, and an artificial intelligence discrepancy model, all the end, let's say, it's very light to be implemented in the target hardware, that in this case was a Texas Instruments C2000 microcontroller unit, with RAM allocation approximate about 1 kilobyte, flash memory allocation of 20 kilobyte, and the execution time for the full code was 170 microseconds, so eligible for the 10 millisecond task implementation for real-time thermal control and the rating strategies. That at the end, it was the final scope of the virtual thermal sensing in order to enhance the efficiency and increase the performance of the overall hardware of the onboard charger. So I have finished with our case on the onboard charger and the presentation. Thank you very much.
Thank you, Francesco. Thank you very much. I would ask also Thomas and Giorgio to join back here. So maybe we can wait and see if there is any question or topic from the audience.
I see the first question from Vicente. Can we use the model in ANSYS iSpec to be implemented in the modelization for the second step? Yeah, we are compatible, for example, with ANSYS Fluent, where you can import directly the MSH file. So the mesh that you have used in Fluent basically can be imported inside Twin Fabrica, and where you can then reuse your high fidelity model. ANSI size spec. I'm not the expert of our parsing procedure, but basically it's constant in pipeline, the making new parsers for, let's say, make Twin Fabrica, let's say, compatible with the different high fidelity simulations tools like Cradle CFD, like ANSYS, like COMSOL, like Gmesh, for example. So also open source, let's say, mesh generators. Or you can directly import the step file inside Twin Fabrica and make the mesh and the finite element analysis directly there.
And I would say we can close this session. Thank you very much for joining again for all over the world. I'm seeing a couple of people joining from different regions. So very nice. Have a great day, afternoon, or evening ahead.
Thank you very much, everyone.
Thank you
for joining.
Thank you, guys. Thank you.
Bye-bye.
Bye-bye.